Understanding the pros and cons of Pythagorean tuning will be easier if we went ahead and constructed a scale based on Pythagoras' findings of pure tone 3:2 musical ratios. We can start anywhere, but the role of the octave plays an important part, so C will be the easiest fundamental note to work with. The process will involve 1. Identify scale notes by making perfect fifth interval jumps away from the fundamental and across octaves. 2. Convert enharmonics to the best note equivalent as needed. 3. Calculate the scaled ratios, a multi-step process of its own. 4. Select the simplest ratios where possible, more on this later. And 5. Rescaling values back to the home octave. First, we need to identify the notes for the scale. We can start by making perfect fifth jumps in one direction away from our fundamental C at octave reference 0. I'll color in C as bright green to keep it distinct from our notes derived from perfect fifth jumps. I'm unsure how many stacks, or jumps, we'll need to make to complete the scale, so let's just go until something weird happens. C to G is our first perfect fifth jump and stays in the home octave of 0. G to D is our second jump, which requires going up to octave 1. D to A stays in octave 1. A to E jumps to octave 2, and E to B stays in octave 2. B to F sharp jumps to octave 3, F sharp to C sharp jumps to octave 4, C sharp to G sharp holds octave 4. G sharp to D sharp jumps to octave 5, and D sharp to A sharp stays in octave 5. A sharp to E sharp jumps to octave 6. Now E sharp is the enharmonic equivalent to F, and we haven't jumped to an F yet, so we'll convert this note to F when the time comes and keep going. E sharp to B sharp jumps to octave 7, and B sharp to F sharp sharp stays in octave 7.
Banjo Dan, I think we hit the weird factor.
Agreed. On to step 2, converting enharmonics. We've successfully circled back to our starting pitch of C with the enharmonic B sharp. We'll use the calculations for B sharp in our scale in place of C since it is a note derived from a perfect fifth interval. But we'll hang on to the fundamental C to serve as a reference point anyway. Let's also convert E sharp to F. Lastly, let's discard F sharp sharp since we already have a G. Since it appears that the scale is starting to repeat itself, let's total up the notes. 12 tones, just like the chromatic scale.
Coincidence?
And 7 octaves, just like the piano.
Another coincidence?
On to step 3, calculating the ratios. Our fundamental, or baseline C, can be listed as a 1-to-1 ratio, and every other perfect fifth located can be represented as a 3-to-2 ratio. They can also be represented as fractions of 3 over 2. If we want to know how every ratio relates to the fundamental at 1 over 1, each subsequent ratio after G needs to be multiplied by 3 over 2 in turn, representing a scaled ratio from the fundamental. They can also be taken to the next power from a fundamental 3 over 2 to the 0th power, which of course equals 1. The G to D stack becomes 3 over 2 to the first power. The D to A stack becomes 3 over 2 to the second power, and so on. Step 4 we need to hold off on for now, more on this step later. These fractions represent the scaled or multiplied ratios of the notes in our scale at every respective octave range they're in. But now we need to rescale them back to the home octave, which is our final step. Since frequencies double at every step up an octave, the baseline C at a 1-to-1 ratio will double its numerator value at every new octave. To rescale the perfect fifth ratios back to the home octave, we need to divide by the octave scale or multiply by 1 over the octave scale, which gives us some pretty impressive ratios, all things considered. Now we can calculate coefficient values, so we can compare apples to apples, and bring them up and over. What we've built is a full 12-tone scale by essentially going clockwise around the circle of fifths. Now let's see here, things are looking pretty good.
Banjo Dan, what's going on at the fundamental C?
Ow!
Yes, we have one ratio sticking out like a sore thumb. The enharmonic B sharp should equal 1.000 like the fundamental C we began with, but it equals 1.014 instead.
I strike! This number is mine.
I'm sorry?
You shan't have this number.
We actually don't want it, we just want our math to equal.
Impossible! I forbid it.
Ah, and herein lies the problem to pursuing a perfect cosmic melody by stacking perfect fifth intervals. The Pythagorean comma. A comma in music is a tiny interval between two pitches. At approximately a 1.014 coefficient value based on B sharp's rescaled ratio of 531,441 to 524,288, which does not equal the ratio at our fundamental pitch C at 1-to-1.
Yeah, but is a 1.014 value really that big a deal? I mean, who's going to notice it?
Recall our conversation earlier about measuring intervals by values of cents. An uncorrected Pythagorean octave totals 1,223 cents, though, or 23 cents sharp. And as we learned on the banjo, 23 cents, or a 1.014 coefficient surplus, is a noticeable difference. So with Pythagorean tuning, the earliest documented tuning system there is, the octave is tempered down to equal a 2-to-1 ratio. To put it in another perspective, a 23-cent offset is about a quarter-step difference. This translates to a small but noticeable fissure between pitches, since even an untrained ear can gobble down a 25-cent difference. It seems like Pythagoras' experiment by going in one direction away from the fundamental has failed.
Wait, Banjo Dan, you said Pythagoras went in one direction. One. What if he went the other way away from C?
You mean if he used perfect fourth intervals leftward of the fundamental C?
Yes, exactly. Is there still hope?
I was actually just about to click the upload to YouTube button. You know what? Let's do the math anyways in the other direction.
Now we're talking. Whoever said music theory isn't exhilarating or fun?
You actually just mentioned that to me off screen just a few minutes ago. You said, quote, Banjo Dan, music theory is not fun or exhilarating, unquote.
Well, I meant after that.
Now we're going backwards, or from right to left, from our bass note, C, making perfect fourth stacks or jumps, and going down octave references and from the right to left for additional stacks, descending into negative octave references. Another perspective is that we're formulating the notes used by going counterclockwise on the circle of fifths, identifying the root notes to the flat keys used in the circle, and in the order that they appear in the circle. Viewing the jumps from left to right will appear as perfect fifth intervals, though. We can take out the skipped over notes. Again, we have 12 notes, and the scale starts to repeat itself past the analog enharmonic of C in the inverse 7th octave. In this chart, we can compare all the unconverted notes derived from the perfect fifth jumps with all the unconverted notes derived from the perfect fourth jumps. Both the 3-to-2 intervals and the 2-to-3 intervals urge us to construct a 12-tone scale, because beyond 12 tones, as we've discovered, the intervals begin repeating themselves. Thus, we must treat the enharmonics as equal in pitch to one another, since we don't have any more notes in Western music to work with. What do you notice about the fractions and coefficient values between methods?
Nothing is equal in pitch. Not a single Slytherin value matches up.
True, but at least they all don't match up equally.
Dividing each coefficient derived by a 3-to-2 interval by its 2-to-3 interval counterpart yields.
There's no such thing as a cosmic melody.
For the fundamentals and harmonics, B sharp's coefficient is already equal to the Pythagorean comma, but for form's sake, let's just divide it by the fundamental of 1.000, and we can divide 1.000 by D flat flat's coefficient of 0.987 to equal...
Silly Pythagoreans.
Yeah.
Well, no one said this tuning system would be perfect.
Actually, wasn't that exactly what Pythagoras was looking to do? To create the perfect cosmic melody?
All is not lost, my dear Watson. There is more work to be done. Instead, we can choose the smallest ratios from both directions to construct a scale with the most harmonious
sounds.
For the enharmonics at C, which one would you choose, Frail Danny?
Neither.
There is something disconcerting about them, to be sure. The Pythagoreans thought so too, so they chose the third option, tempering the enharmonics B sharp or D flat flat, to match the fundamental of 1.00 or its octave at 2.000.
Isn't that like cheating?
Tempering, Frail Danny, tempering. Tempering the last interval avoids the sharpness from the 23.5-cent Pythagorean comma and ensures the scale fits tidily between the octaves. The concept of tempering will be used for the rest of music theory history, up to and including the present day's equal temperament. So, it's a thing.
Okay, got it. Math is more of a guideline than a hard and fast rule.
Now we have all available notes with the simplest ratios for the Pythagorean scale. The left-hand column contains the original note values, and the right-hand column shows their assumed note values.